Well, hello everyone, and welcome to another Renewable Energy Speaker Series hosted by the McNeil Center for Applied Renewable Energy, or CARE, here at Concordia University of Edmonton. We are recording the webinar, so if you prefer to not have your camera on, please feel free to turn it off. The recording will then be posted on our website for you to refer to when you'd like. I'd like to also ask that everyone please keep your microphone muted just to avoid any background noise. This speaker series provides all of us an opportunity to explore renewable energy solutions, learn about the challenges faced by the sustainable energy sector, whether that be industry, government, and society as a whole, as well as careers in the renewable energy sector, and interact with experts from across Canada and beyond. So before we begin the seminar, I'd like to acknowledge that Concordia University of Edmonton, today's host, is located on Indigenous lands and territories, now called Treaty 6 territory, and the homeland of the Métis Nation District 9. The North Saskatchewan River has been a significant place for the Blackfoot, Dene, Nakota Sioux, Cree, Saulteaux, and Métis since time immemorial. We honor and respect the agreements made by our ancestors to live in good relations for as long as the sun shines, the grass grows, and the river flows. I invite you to also do your own acknowledgement with the territory where you're located. Today's webinar is titled Lunar Exploration and the Path to Mars. So excited. The global space community, including Canada, has come together in an effort to return humans to the moon. Lunar exploration is a vital step and testing ground to advance human space exploration, scientific discovery, and technological innovation in preparation to one day reach the surface of Mars. It will build expertise and the confidence needed to ensure future mission success. This presentation will explore the motivation for these lofty goals, touch on some of the scientific discoveries and milestones reached thus far, and the ambitious plans for the future exploration of the moon and Mars. Well, today's speaker is Dr. Cassandra Marion. A lifelong explorer, Dr. Marion completed her PhD in geology and planetary science and exploration at the Earth and Planetary Institute at Western University. Her studies focused on meteorite impact craters and lunar and Martian analog environments in the Canadian Arctic and subarctic. Dr. Marion has also participated and led a series of simulated robotic and human missions designed to learn, train, and prepare for real missions to the moon and Mars. She has more than a decade of experience in education and public outreach, developing and delivering science programming. In her current role as science advisor for the Canada Aviation and Space Museum in Ottawa, she acts as a science communicator dedicated to sharing her passion and knowledge of Earth and planetary science with communities near and far. After the presentation, I will come back to facilitate the Q&A. For now, Cassandra, over to you.
Well, good afternoon, everyone. Well, it's afternoon for me. It's about 2 p.m. here in Ottawa. So I am currently at the Canada Aviation and Space Museum in Ottawa, which is on the traditional and unceded territory of the Algonquin Anishinaabeg people. So I'm very humbled to live and work and talk space on this wonderful land. And I'm so happy to join you today. Thank you, Carla, and thank you again, Cam, for instigating this invitation. I think I should point out, even though you just read my bio, that as much as I'm going to, as much as possible, drop some renewable energy, or at least energy topics, little nuggets throughout the presentation. Note that I'm not an engineer nor an energy expert, so I will do my best but I won't go too far down the rabbit hole. But what I am hoping to do is give you sort of a picture of what is happening in lunar exploration right now. Where does Canada fit in? And what does this mean going forward? Like, what are their big goals and where are we? And how does that compare to Apollo times? So I don't know if you remember, but it's 1972 was the last time that humans landed on the moon. That's over 50 years ago. And now they want to do it again, but their goals have changed and their approach has changed. So how is that and why is that? So we're going to get all into that. The major differences, this time is that it's an international collaboration. It's not just one nation going that's, competing against another individual nation, where it was like US versus the Soviets at the time. Now we've got more than 60 nations that are working together, and not just nations, but commercial partners. So we've got companies, enterprises that are partaking, and they're all coming together, going together to basically get a sustainable presence, a human presence, and a robotic presence on the surface of the moon, with the hope and the end goal that we're going to equip ourselves with new knowledge, get our technology up to the levels that we need it, and quite literally get the fuel to push us forward onto Mars. So that's really the hope for the Artemis program that we're going to get into. So I'm going to bounce around a lot, from science to energy to some spacecraft. So bear with me as I bounce around. I hope I keep it so that I don't lose anybody. But we'll probably start with a little bit of history, then we'll hit some science, and then we're going to talk like what is actually happening and where those energy sources are. All right, let's see if my mouse will work for here. Elaborate for me. Woo! All right, so the way that we generally do space exploration, this counts for any body in the solar system that we're going to go and visit. We advance in small increments. So, we start by developing our rockets. If we're going to go explore a very new body, we first put an orbiter in orbit, and we explore, remotely from that perspective. We get as much information as possible, mapping for where to land next time, for example, or what is safe. Is it even feasible to land? What questions do we want to ask? Should we spend the money to go further to land, or to explore by rover, or to send humans? So every time it's incremental, and it's asking the right questions, and then developing a mission to answer those questions. So we basically go rocket, orbiter, lander, then rover, so we become mobile on the surface. Once we've checked all those boxes and we've really described the environment and we're comfortable and we think there's a reason to go, there's a questions to be answered, and it makes sense to go, then we get to the stage of developing a human-rated capsule, a human-rated lander, and then, walking on that other surface. Of course, we've only gone on the moon so far, but the approach will be the same for Mars or any other body. And then if there's more questions to answer and you can do it sustainably, then we get into the potential to building sort of more infrastructure that is in a more permanent way. So always incremental, and that goes the same for not just the spacecraft, but every piece of technology, whether it's a piece of hardware that's going to, like a robot that is harvesting in a lunar greenhouse, or in environmental control. Every little piece is developed in increments that way, where it's always the engineering process, design, test, analyze, repeat until you get it right. Then we start testing in space to prove that it's usable, and then we put it on a mission. We typically, through time, we will reuse older technologies that we've used in space many times that we know work, and we're confident in them. So they have their heritage technology. We tend to use more of that than sort of novel pieces, because they're more reliable. And things like Canadarm, our robotics, we repeat the same sort of approach to our robotics because they work, they're reliable, they're robust. So you'll see that repeating in anything that we talk about. When I do drop little energy nuggets, I want to emphasize that the return to the moon, as much as we want it to be sustainable, I want to pinpoint that we don't always mean renewable. And I'm sure this crowd knows this far more than I do, but I felt it necessary to point out that these terms are often used interchangeably, but particularly in this approach, we don't necessarily mean renewable as resources that won't run out. They're sources that naturally replenish themselves on a human timescale, at least, things like solar. And then sustainable is, we want to, our approach to energy, for example, would be responsible. It's focused on the long term. We try and minimize any environmental impacts. minimize any economic drain or slash damage, and meet the needs at the same time. But it's always sort of long term. So sustainable nuclear power would satisfy sustainability, but not renewability, because that's the definition of not renewable power source, right? Because it decays, and then that power, that isotopic source is gone over time. And so how do we make lunar exploration sustainable? And oh, sorry, my mouse won't move onto my screen. Sorry about this, 2 seconds. Oh, there we go. Okay, I got it. Woohoo. All right, so how do we make lunar exploration sustainable? It's always this long-term approach to establish this permanent human presence with the goal of eventually going to Mars. But that's really a ways down the road. But their approach is reducing reliance on Earth-based supply chains. So any basically material or source, whether it's like oxygen, water, food, etc., everything we want to be able to get in situ. So we call those in situ resource utilization, or probably or ISRU. That's going to come repeating a lot. Fostering a lunar economy, so making things cheaper by sharing the bill, by including others to make it collaborative. It's an international effort, and especially, they say the space industry in the next decade is going to, is in the $1 trillion levels of sort of on the business side of things, which is not my area. But it is, they are making a profit. There are definitely commercial companies that are going to make a profit on developing these technologies and so on. So there is a draw for it there. And if you are fostering a lunar economy, you're helping to drive the sustainability of the whole. All right. And there will be, a mix of renewable and non-renewable power sources used throughout, and have been in the past. So I'll try and touch on Apollo days as well. So speaking of the past, this is a very giant graphic with tiny text. So don't try and read any of the little particulars. The point is really just to see where there is busy and where it's not. So the top left here, you see 1959, and then it goes further in time going to the right, and then again bottom to right. So I want 2 points to make with this slide. And the first is that even though we landed on the moon, and I say we as the human race, but the Americans landed on the moon in 1969, there were 21 missions, spacecraft sent to the moon before that ever happened, to investigate, like I said, orbiters, landers, rovers that investigated the surface and checked all those boxes before they ever sent humans, even though it was a really short amount of time, because they only started sending in 1959 and then they landed 10 years later, which is mind-boggling, in retrospect. But you'll see that along this time, yet a lot of those are the Apollo spacecraft, but there are also lots of lunar landers on them. Then that program got shut down. Space race over, mission accomplished. Their goals were very different at the time. It was a technology demonstration. It was a geopolitical, issue. But the scientists never stopped wanting to go back to the moon. The scientists, globally, we're still researching these rocks. We're still examining, trying to learn more and more about the moon, because the moon is really a time capsule for the history of the solar system. I'll touch on this a few times, but there's just so much we don't know and that we could know, and more we know about the moon, it means the more we know about Earth and Earth's past, which is our past. So there were spacecraft that we started sending back to the moon, specifically in the early 90s, and then ramping up in the early 2000s, especially. I'm going to point out this Lunar Reconnaissance Orbiter here that got launched in 2009. It has been taking these beautiful high-resolution images of the surface since then. It's still going strong, and we're still collecting so much more data. You'll also see more international interest. So in the years 2000 and onward, you've got a Japanese orbiter being sent, Indian orbiters being sent, European rockets being sent, so on and so forth. So it's becoming more international, and sort of globally, our knowledge is increasing as we're exploring. And then you'll see all of a sudden increase again, and that is the return the agreements internationally to return to the moon. It's only accurate about up to this line, but there's going to be a lot more dots and spacecraft to come. So staying in the past, I don't know how familiar you are with Canada's role in the Apollo program. We actually had many. So I almost love this slide because it usually surprises many folks, particularly from the younger generations. And I wasn't around when Apollo was launching, so this was new to me at some point. But we've got 30 some odd, I'm going to say there were 30 Canadian/British engineers that joined NASA's Space Task Force after the Avro Aero program, which was a supersonic jet that we were developing, an anti-missile jet. Of course, I'm at the Aviation Museum, so I'm going to talk about an aircraft. But that was in development in the late 50s, and it got canceled. We all call it Black Friday in 1959. And 4 months after that program canceled, we had our best and brightest engineers, Canadian and British, working together on developing this aircraft. And then they were out of a job all of a sudden. So NASA scooped them up, and they helped us get to the moon. And some of their names, Owen Maynard, for example, he became chief systems engineer for the lunar landing module. And he was in mission control along with many other scientists that worked in Gemini program and so on. So there were a lot of Canadians involved, just not as well known. We're also a Canadian company called Eru in Quebec City, which still exists today, developed 9 out of 10 pieces of the landing gear for the lunar modules during Apollo. Not the foot pads, so we can't say we're the first to step on the moon, but there are 24 Canadian legs on the moon. And we also have trained some of the Apollo astronauts at in Sudbury here in Ontario in geology and some analog missions and testing of some of their instruments, but we test them there. And today, Jeremy Hansen, who's going to be going to the moon, and all of our Canadian astronauts and many continued American astronauts, they now all get some of their geology training in impact craters here in Canada. And I'm very honored to say that I got to participate in some of a very small part of that training. So here's looking at the moon Apollo program. They landed 6 times on the near side of the moon, so the side of the moon that's always facing us. And again, incremental. The first time they landed, they were only on the surface for about 22 hours. They slept most of that time, and they only actually exited the module for about 2.5 hours. And then if you look at the last mission, it increases each time. They were on the surface for 75 hours, and they walked around for 22 hours. So each time they're getting better, they're getting more comfortable with their technologies, and then the risk factor is going down as they improved. I'll also point out that, landing only 6 tiny little spots and covering a very small surface area of a very large moon, it's about quarter size of the Earth. You're not actually, it's wonderful that we've explored those and we've got samples back, but on the whole, we still have just a pinpoint view of the moon, from the surface. So going back from a scientist standpoint, there's still so much we have to learn. Today, there's still several orbiters around the moon. There's even a rover on the far side. China's got a rover U-22 that's still driving around. There's been 7 lunar rovers total, but the other ones are no longer active. So anyway, all right. But the moon, it's billions of years of history wrapped in a ball. These are a couple of images each of the Apollo landing sites, just to show you a little bit what they look like. So Apollo 1 here, you can see the lunar landing module. It's the Lunar Reconnaissance Orbiter. It brought its altitude down to about 22 kilometers and took these high resolution images really, really close. So here's proof for everyone doesn't believe in the lunar landings. We can literally see that we've landed. The modules are still there, and you can even see the footprints. You can see the rover prints for Apollo 15, 16, 17, they're still there. They had, there was pretty short missions. They stepped outside. They set up these surface experiment packages. So seismometers, magnetometers, antennas. mirrors, and so on to collect data and continue collecting data even after they took off. So a little nugget for the energy folks. The Apollo spacecraft itself, it was primarily fueled by an oxygen, hydrogen, alkaline fuel cells. That's for its electrical power. And it was located in its service module. And then they combined the fuel cells with cryogenic hydrogen and oxygen to generate electricity and potable water for the crew. The lunar landing module, though, did not use fuel cells. It used silver zinc batteries. I think there were something like 5 or 6 on the descent module and a couple on the ascent module. They also used, so these lunar surface experiment packages, they need to be powered as well. And also, it can be extremely hot or extremely cold on the moon. And so the very first, the Apollo 11, they had brought a combination of a radioisotope heater unit, basically like a little nuclear heater, plus a solar cell to operate those instruments. And then every year after that, they switched to what they call the SNAP 27, which is a radioisotope thermoelectric generator. So another nuclear generator that just converts heat energy from radioactive decay to electrical energy. And that's what powered all of these instruments during the Apollo days. And we still use, and I'll show you a graphic after, but we still use RTGs across the solar system. They're wonderful power sources that last, they can last decades depending on the size and the approach, but they can last decades, and you don't have to worry about, when you're in sun or not. And I'll point out that the Voyager spacecraft that were launched in the 70s that are still going, they have power because of RTGs. So, all right, so that's what the RTG looked like for Apollo 11. And then the other instrument that got put out, I'm just checking my time here. Okay, that got put out are these like mirrors where they call them retroreflectors, and we can send a laser beam to the moon. They bounce off that mirror and come back, and we calculate using time of flight the exact distance between Earth and the moon. And we've been doing that and continuing that calculation ever since because they're still there. There were 3 different Apollo missions that put them down, so we can double check at different locations from the moon. And we were able to ascertain that the moon is actually moving away from us at about 4 centimeters a year. I'm going to come back to that point and show you how close it once was. What have we learned so far? There are 5 major things from those rocks. We've got ages, the different compositions, like the mineralogy on the moon is not that different from the Earth's, quite similar. The moon was once covered by a magma ocean. The lunar surface is covered in what we call lunar soil, but there's no organics. We call it regolith. It's like broken up material. It's just been mashed up and bombarded by space rocks, collisions over its formation, and then 4 billion years worth of impacts, and it's chewed up the surface of the moon, and all of that material kind of redeposits down. And so the surface, like up to 10 meters of it, is actually loose, a very unsorted sort of rocks to dust and everywhere in between. We also confirmed that there are lava flows on the moon. So I'll show you what that looks like in a minute. And with all of that information, we also have a much better idea of how the moon formed. There's what we call the giant impact hypothesis, where a Mars-sized object slammed into the moon or slammed into the Earth, and then sort of knocked off a good hunk of the mantle and the crust of the Earth. And all of that material became sort of debris in orbit around the Earth, and as it condensed, it reaccreted into what is now our moon. The object was called Theia at the time, and when that formed, it was much, much closer to the Earth, about 3 Earth radii away. Okay, so it would have been, if you were standing on the surface of the Earth, which would have been way hot and you wouldn't have survived at the time, but if you were and you looked up and saw the moon in the sky, it would have been 16 times larger. So much, much closer, just to give you some context. So like I said, it is now on average 380,000 kilometers away, but it once was much smaller. So it would have been, it started at 3 Earth radii, and now it's at about 60 Earth radii away. So half of Earth's width or way. We also, so the moon is tidally locked to us. We always see the same face, and that's because when it formed very close, and so it became gravitationally locked. And it once, after its formation, it was completely molten. We know that because of the distribution of the minerals on the surface and the types of terrains that are there. We know that those minerals, as they formed, they basically segmented, they divided. We call that differentiation in the geology world, where lighter minerals went to the top and heavier minerals went to the bottom. And so that you can see that in the rocks and in the samples that are returned. So if you look at the near side and the far side, you can tell there are very significant differences. One is covered far more cratered than the other. So the far side, this is the side that we never see. It's not the dark side because the moon does have equal days and nights everywhere. 14 Earth days, 14 of day and 14 Earth days of night, because it goes, basically it rotates once on itself at about the same rate as it goes once around the Earth. So we don't actually see it rotating, but it does. But these light areas, that is the ancient lunar crust. It's very rich in silica, oxygen, calcium. And then these darker regions we call the lunar mare or seas for mer. And they are actually produced by ancient lava flows. There was volcanism. There were volcanoes on the moon that erupted, and the lava filled these giant ancient basins. So the moon is no longer active. It's been the last dated volcanic rocks on the moon, at least that we know of, but again, we have limited samples, was 2 billion years. And so it's been at least 2 billion years where there's been no change. Whereas on Earth, we've got plate tectonics, we've got erosion, we've got glaciation, major activity that completely resurfaces our crust. And so we have very little in terms of rocks and history and information hidden in the rocks that has survived where it has on the moon. So we can learn not only about the actual history of the moon, but history of Earth by studying the moon. We've got spacecraft that collected digital elevation collected elevation data and made a digital elevation model. So this is the topography of the moon. The range is very similar to that of Earth. There's only about a kilometer difference. Both of the highest mountain and the lowest valley are on the far side of the moon. This large region here is called the South Pole Aitken Basin. It's the largest impact crater on the moon. And the return to the moon is actually hoping to go to the south pole of the moon. So it'll be very different because we normally landed on the near side, which is physically much simpler than getting to the south pole, but I'll explain why we're going to the south pole. I'm not going to go into detail here, but just to say, we do have a lot of instruments that showed us that the moon's chemistry is very complex, very dynamic, and there's so many rabbit holes to go down. But I'm going to be quick on these ones. We also used impact craters and their density, how many there are. We call it crater counting, to determine sort of a combination of absolute and relative ages of the surface of the moon. And then we use that scale to estimate ages of the surfaces of all the other solid bodies in the solar system. So like the surface of Mars, the surfaces of some of Jupiter's moons, things like that. And because we do have some ages from the samples we returned, we can have some semblance of accuracy for those craters. This is up close what some of those very beautiful high resolution images look like. These are just 2 impact craters on the moon. So just because they're pretty, I thought I'd show you what that looks like. Okay, in situ resource utilization. Within the rocks, within the regolith, which is that sort of loose material at the top, full of rocks and dust and things, there are a variety of minerals, volatiles that we can use going forward. The number one and the main driver for this return to the moon is water in the form of ice. It's located in these permanently shadowed regions, which I'll talk about shortly, but it really is the driver. The why, because you can extract it for life support, so drinking water, breathable oxygen generation. You can use electrolysis and turn it into hydrogen oxygen for propellant. You can recombine hydrogen and oxygen in a fuel cell. It's making your electrochemical device again that converts that chemical energy from the oxygen, the combination to create power. Sorry. And then you can also, you're producing water when you're doing that. You've got as your byproduct without combustion. And then if you're breaking up water ice into oxygen and hydrogen, that is liquid oxygen, liquid hydrogen. That is the most powerful, basically rocket fuel that we have, and that is what is fueling the rocket that is getting us back to the moon at this time. So the idea is if they can get to that water ice, they're able to extract it, mine it, and use it efficiently, then it's a lot easier to launch off of the moon than it is to launch off of the Earth to get to Mars. And that's really their end goal, because if you have to take so much fuel with you off the Earth, because the Earth is a much bigger gravity well, and it's got the atmosphere to contend with, it's just way more expensive, and it takes more fuel to get more fuel off the Earth than it would on the moon. And so we can not only perfect all our technologies and our approaches, but we can use those resources not only on the moon, but also to get off and go beyond. And that's really what's driven most of this international interest and sort of where the dollar signs are coming from. Lots of other options in these permanently shadowed regions. There are a variety of volatiles, so that's sort of gaseous things that are frozen into the rocks: hydrogen, nitrogen, sulfur, helium-3. I'm not going to go too far down the rabbit hole, but they want to make nuclear fusion power using helium-3. This has been proposed where you combine helium-3 with deuterium, or smash them together, essentially. It is still in development. I'd say we're, from what I understand, again, not an expert, decades away of making that really work. And there's also the question there: is there really enough helium-3 on the lunar surface? So it accumulates. It's deposited through solar wind, and it does accumulate on the lunar surface. But you'd still need 60 tons of regolith to get 1 ton of helium. So a questionable practical approach. In the minerals, most of the minerals are actual oxides. And so if you could break those elements down, the main mineral that covers most of the moon is actually 40% oxygen. And it is possible to pull the oxygen out of the rocks. It can be done in a lab here. It would be challenging to do it on the moon, but not impossible. And so the same thing with all of those other elements. I'm sure you can see where you can use titanium for shielding, or aluminum, etc. So there is a lot on the moon that we could potentially use going forward. And then, there's huge benefits, right? You're reducing cost if you're using stuff that's already there, but then there's also that initial cost to get any of the infrastructure in place to use it. And so there's sort of a weighing the balance between the two options. So getting our technology readiness up to the level where we have the techniques to extract it. There are other challenges, things like electrostatic dust and things like that get into every instrumentation. So there's lots of challenges, but everything is in the realm of possible right now, and they're around the globe. We're testing technologies and testing how to basically extract these individual pieces and how they can be used. One of the examples, and I just threw this in there because it's one of my favorite models, is using the regolith itself to make something that they're calling lunarcrete. So you're making concrete blocks. You can either make concrete blocks out of the lunar regolith. You basically just need a heat and a binding agent, and you can make that happen. And they are doing that in labs today with lunar simulants mostly, not with actual lunar rocks. We wouldn't waste them on that, but with lunar simulants. And you can also use it as material in 3D printing. So this is one of the European Space Agency's concepts of a lunar habitat that's 3D printed, and then a robot would come around and 3D print basically the radiation shielding over top of the habitat using the lunar regolith. All right. I think I'm going to blow through this. There is a water cycle on the moon that's generated by meteorite impacts, like micrometeorite impacts. And then they basically, all that water is thought to accumulate in these permanently shadowed regions. So the moon, unlike Earth that's tilted 23.5 degrees, is only tilted about 1 degree, or 1.5, something like that. So very, very small. And so the poles, even though you get full 14 days of daytime, 14 Earth days of night on, equator, the mid-latitudes on the moon, when we're talking about the poles of the moon, the sun just hangs out in the horizon and comes around all and just sort of hovers and bounces around that horizon all through the year. It does have a winter-summer phase where it's a little bit darker and a little bit lighter. But there are these regions as a result that are like the low topographic regions that basically stay in darkness permanently and have been for over 4 billion years. And so volatiles can accumulate in these dark regions. The reason why water won't survive on the surface otherwise is in the daytime. If you are in the sun on the moon, you can be at temperatures from anywhere 150 to 200 degrees Celsius. But if you're in the shade, it's the reverse. You're at like minus 173 degrees Celsius. I think the lowest temperature we've measured on the moon is about minus 221. So then all of those volatiles, they are sticking and staying in their solid icy form. So this is just a graphic showing where all of those permanently shadowed regions are. The South Pole, the dot would be about there where my cursor is, on the edge of Shoemaker Crater here. And this is an instrument that's showing hydrogen concentrations in that same area. And you can see how the permanently shadowed regions coincide with the hydrogen concentrations. There is, I think, 5 or 6 instruments now that have confirmed this information. So they're pretty confident that there's water ice with the first discovery of this in 2008. All right, this is a video showing you if you're going to go through 2026. The map of the moon in the back is real, but it is a visualization, an animation, so not an actual image. So it's computer generated of what the illumination would look like around the South Pole. So again, this is the actual pole and Shackleton Crater. And this is where they're hoping to go back to the moon to land. You can see how there would be impacts if you wanted to put, let's say, a solar array on some of these in this region. If you were going to land like over here, for example, you're going to have periods of time where it's in darkness, periods where it's in lightness. But if you're at the top of the hill, for example, you could significantly, it is feasible to put solar power there at the top of the hill, especially if you can put it even higher. They're thinking like 10 to 20 meters up, these giant vertical panels. Because it's better to get, let's say, 3 to 10 hours in a row of darkness versus 14 days straight of darkness, because that's more reasonable to generate and store your power. We're going to go back down that rabbit hole, but I just wanted you to have like a full idea of it's going to be tough. And then they're going to be living and working in a region where they're going to feel like they're in darkness a lot. There's never going to be like full sun on them if they're working and living in these regions. And then they're going to be sending rovers and stuff. So everything is working sort of in low light or in the dark. All right, so the Artemis return. What time is it? Okay, we started a little late, but I'm going to breeze through this. The Artemis program as a whole, they've got 3 missions that are, well, actually, yeah, Artemis 1, 2, 3, 4, 5 or so are planned fairly detailed. Artemis 1 was a test flight. Artemis 2 is going to take our Canadian astronaut, Jeremy Hansen, around the moon, just a flight test around the moon. And Artemis 3 is boots on the ground. This is the poster that's on the front of the museum here. So like I said, there's like 60 countries that have agreed to go back together. Russia and China aren't on the list, in case you're asking. But most other spacefaring nations are, and have all agreed to do this peacefully, to be transparent, to release data, open sharing, and then protect heritage sites, be environmentally conscious, things like that. The idea is to put a space station around the moon in what's called a near rectilinear halo orbit. So it's this weird elliptical polar orbit. And that will stay there. So it's basically a working habitat in orbit around the moon. And then the Orion spacecraft, which will be launched on the SLS rocket, that will basically ferry astronauts back and forth to and from this station. And then another lander will go from the station to the surface. Artemis 3, because the space station's not quite ready yet, it's actually just going to meet right up, like Orion will meet right up with the lander and have him go down. So that's the overall idea, is like a space station and then a series of spacecraft that basically get us from the Earth to the moon and then from lunar orbit to the surface. Canada's contributing Canadarm3 to that space station, and it is due to that contribution that we got 2 seats on future Artemis program, and the very first one is our seat on Artemis 2 to fly by the moon, which is really special because that means we are the second nation to have our citizen go beyond Earth orbit ever. Because only 12 Americans, actually no, 24 Americans have gone beyond Earth orbit. 12 have walked on the moon, but no other nation has sent any of their astronauts beyond Earth orbit. So we will be the second. That's pretty legacy building for Canada's history in space. If you have more questions about Canadarm, I can ask those later. Space launch system, like I said, liquid oxygen, hydrogen fueled. The Orion capsule, crew capsule is up here, and then it's got the service module underneath. This is its main core stage with 2 boosters, and this is the interim cryogenic propulsion stage. So it's kind of like the little upper stage, kind of like the baby stage. All right. So Orion itself, if you're curious, the rocket itself is expendable. They did recycle the engines from the shuttle program. So it is using some components from older historical programs. The Orion capsule, they do plan to reuse portions of it, like the avionics, switch panels, crew seats, flight computers, mostly avionics, things like that. And then as time goes by, they hope to reuse more and more of it going forward. The service module here, that's the power and propulsion unit for Orion. And it basically separates from the crew module just before it comes back to Earth. I can answer more specific questions later. The Artemis 1, so it already flew. This is a selfie. So Orion actually had some cameras on its solar panels. Orion is entirely, mainly solar panel. It's like this X-wing configuration of solar arrays that convert sunlight into electricity, as you know. So that's its main power source for electricity. And so it took a selfie with itself and the far side of the moon, which is pretty special. There are a series of them. So if you want to Google them, there's so many, with some with Earth in the background. They're so pretty. This was its launch. Anyways, it was a big success. They did learn some lessons. There were like little issues with some electronics, a little issue with the heat shield. So that was the main thing that they wanted to get straight, why they delayed the second mission for a little while. And then Artemis 2, which is potentially launching as early as next Friday. They're basically doing their wet dress rehearsal this weekend. Is going to do a figure 8 around the moon. It's going to launch in orbit around the Earth. It's going to do a practice run of a docking approach. So the Orion spacecraft is going to separate from that upper stage. It's going to turn around and then pretend that it's going to approach to dock with its upper stage and then stop just before it gets there, because they're basically testing the navigation. And then if everything is okay for all of the environmental controls and everything in the Orion capsule, then they're going to raise their orbit around the Earth, do a trans-lunar injection burn, so fire the engines basically to get them to the moon. And that one engine burn is basically we call it a free return orbit. It gets it all the way to the moon, use the moon's gravity well to get us all the way back. They might fire, they might do like little micro burns just to adjust their trajectory. But this burn over here that it does just on its way out is the one that gets it all the way there and back. This is the crew. So we got Jeremy Hansen, our Canadian, and then 3 Americans. This is the commander, Reed Wiseman, Victor Glover, and Christina Koch. Jeremy's the only one who hasn't been to space yet. Christina and Jeremy are the mission specialists. And then we also have another Canadian astronaut, Jenny Gibbons, who is Jeremy's backup. So for some reason, he wasn't able to fly. She would take his place. And even though she probably won't fly, because he will, she'll be in mission control. She's one of the Capcoms, and has been training with the whole crew and one other American backup since pretty early on in their training. They've been training for a couple of years now. So they are ready and raring to go. If you're curious about what Jeremy's mission patch looks like, this is the one, and then this is their crew patch. Their rocket is on the launch pad, ready to go. This is the potential launch windows. So like I said, next Friday, 9:41, they're all evening launches. That's the potential first flight if everything goes well with all their testings over the weekend and early in the week. So fingers crossed. There is a lot of science. I'm not going to go down this rabbit hole unless you ask, but they are doing some science experiments, mostly them being the guinea pigs, and they're going to do some lunar observation. So basically geology photography, if you will, astrophotography, looking at craters and lunar ice and so on, and also just investigating spots for potential landing for Artemis 3. There's a rideshare program. So between the cryogenic module basically and Orion, there's this ring that has a bunch of CubeSats in it from different countries. There's a German one, a South Korean one, a Saudi Arabian one, an Argentinian one. And so we're doing a rideshare program, another way of making it a little bit more sustainable, a little bit more efficient in like multitasking. The rocket is sending multiple payloads up at once. So it's not just Orion that's getting put into space. There are, I think, 10 CubeSats going with it, doing different things. This is the overall plan for the surface operations. I know I'm like getting short on time now. So again, incremental, where they basically establish themselves on the ground. And there'll be several missions in before Gateway's fully up and running. They start getting more vehicles on the ground. Some of them are just logistic vehicles. Then they turn into kind of dune buggies or like moon buggies. And then several missions in, they would establish their first power element, which is probably going to be these vertical solar panels that they combine. They call it regenerative fuel cells. So they have a combined solar panel and a fuel cell. Explain that a little bit in a bit. Early on, and then eventually they actually want to put a fission nuclear power plant going forward for future moves. If they do plan to like get into extracting lunar resources and manufacturing and things like that on the moon, they're gonna need a lot more power than like a few solar panels can provide. So just thinking long term, that's what they're going to start with. So like a combo of solar and fuel cells, and probably for different instrumentation, they'll have more RTGs. And then in the long term, they've already agreed between the U.S. government, they're like defense group, DOE, I think it's called, and NASA. They've already agreed, and they're developing how that would go. Okay. So Artemis 3, they're going to meet up with the lunar lander, do this really funky polar orbit, and then go down from there. I can answer more specific questions if we have time at the end. I just don't want to take up too much time. So the lunar landers, Artemis 3 will be delayed a little bit more because the actual landers, the one that are going to meet up with Orion around the moon and then bring them down, because Orion does not land. It only plops into the ocean when it comes back to Earth. They're not ready yet. They're in development. I mean, Starship is a ways ahead, but they still have to do a lot of testing. There's still a lot of unchecked boxes before these guys are going to be ready to go. So they're going to be delayed probably by a few years before we get to go in these low light conditions and walk around the moon. One of the other ways in making it sustainable is this is like all of the human missions, but we're sending a series, and I mean internationally, a series of robotic missions. And there's a program called the Commercial Lunar Payload Services. And again, It's a giant ride share program where you can get, it's a lot cheaper to get sort of a small payload to get to the moon if you're sharing the rocket, if you're sharing the cost. And so this is just examples of a series of missions that are going to be going up on this payload services. So you get one rocket that might send, anywhere from 2 to 10 payloads at a time. So you could send multiple rovers, multiple satellites on one rocket to get to the moon. And that includes Canada's Lunar rover that's in development that we hope to launch 2028, 2029 on one of those launches. And the same thing with our Lunar Utility rover. Setting up camp. First thing they're going to have to do when thinking long term is how are they going to power it and how are they going to communicate? So I'd say power communications are top of the line important. And the approach is going to be super important too, right? So not just power generation, let's say you've got solar arrays, but also how you're going to distribute that power, because there are multiple different, you might have a habitat, you might have rovers, you're going to have multiple different units that you have to get the power to. And it's not like they're going to set up a giant power grid early on. And so there's a lot of questions about the approach on how they're going to power that, the different systems. This is an example of the actual image of one of those solar to fuel cells. So it would be the regenerative fuel cell is like a closed loop system. So they use solar energy during the day to produce hydrogen and oxygen via electrolysis. And then they recombine it in a fuel cell to generate electricity and water during the night. And then that just runs on a loop. And so again, depending on where they are, there's either 14 days of day and night, or there's those low illumination sections. So if they raise these solar cells up, that's the thinking. There's a lot of challenges though, because you'd have to you'd want, again, even just for the solar panel, you want it to be mobile, you want it to be able to rotate, to follow the sun, things like that. But then there's dust and stuff like that that gets into everything. You're in a vacuum, so low pressure environment. You've got huge temperature swings between day and night. And so there's a variety of approaches. And then I thought I'd throw this example in here of one of the solar panels that was taken off of the Hubble telescope when it was repaired. This is a micrometeorite or space debris impact into the solar panels. And they took them down and they replaced them a couple times actually. Just to give you an idea. And so because, Earth from micrometeorites, we're protected by our atmosphere, but the moon doesn't have that. And so these solar panels, they're going to get hit over time. So I think I'll stop there just because I know we're close to 3. Maybe I'll just show this one because I did say I'd talk about RTGs. Because I can go down many rabbit holes, but I think I want to wait for questions to go down rabbit holes. I just wanted to show you the different missions that we've used. Basically, these radioisotopic thermoelectric generators, little nuclear generators, often just as heaters to keep the instruments warm, while the spacecraft also has solar panels. But also any mission basically that goes beyond Mars, we tend to use nuclear just so that you keep getting enough power as you're going further and further away from the sun. And so there are just almost every body in the solar system we've used them on, and both the operating rovers, Curiosity and Perseverance, run on our Chi-Chi power today. And because we learned our lessons trying to use solar panels early on. So there's the pros and cons to using the renewable energy in space. We try and combine it as much as possible, but it's always a balance between needs and practicality. Anyways, so I'll stop there because I don't want to go too far down my rabbit hole.
Thank you so much, Cassandra. Wow, I am blown away about so many things. We only have a few minutes, so we have time to take one question. If anyone has a question, feel free to put it in the chat or just raise your hand. But what I will say is I think there is so much potential here for future discussions. So I will reach out to you, Cassandra, and hopefully have you back in the future to talk about some of these. There's so much in here. My God, I'm kind of blown away as to what's happening. This is incredible. And also just some of those options and possibilities that are being explored to use some of those resources on the moon to take us beyond. Does anyone have one question that they'd like to ask? I do realize we're near the end here. Yeah, there's one here. Here we go. There's one from Licia here. Thank you, Dr. Marion. Great presentation. My question is, as we move towards building on the moon and Mars using lunacrete, what are some potential risks, both for the safety of the astronauts and for the preservation of the lunar environment itself?
This is a really, really good question, and it changes depending on approach. And these discussions, we don't have all the answers yet. Those discussions are still being had. The lunacrete, they're still establishing, how best to do that. If you're going to make the lunacrete, for example, you're going to need some heat. So you can either generate that heat, or you can, refocus solar power or solar light as for smelting or for sintering, for example, more accurately. And so, thankfully, at least on the life side of things, we haven't yet found any organics on the moon. So we're not worried about contaminating any sort of life forms. But no matter what we do, if we start digging up the moon, just like we would anywhere on Earth, we want to do it in a responsible way. And so they're having discussions now on how you're responsibly excavating that regolith, where you would use it, how you would install things. I didn't get to go down the rabbit hole of even just waste management, everything from human waste to spacecraft. Every time we stop using something, we just kind of leave it, and it becomes a spacecraft graveyard. So can we reuse those things like that? But then they want to protect those heritage areas. There's so many rabbit holes to go down. So valid question. I don't have a simple one answer for it. But on the safety side, lots of potential risk, especially. So thankfully, you're not worried about things like air contamination, because the astronauts are not breathing the air next to different instruments and things. They're in their self-contained suits, or they're in their self-contained habitats, which are extremely controlled environments. So there's an aspect there, but there's always going to be a level of risk to each approach, and everything they do, they will only get an astronaut to do something if it cannot be done by a robot, so that they reduce the risk as much as possible. The same thing, we do the same approach on the International Space Station, for example. They won't send an astronaut out for an EVA to go and fix something if Canadarm and Dexter can fix it, or Canadarm2 and Dexter can fix it. So they will get robots to do everything possible, so that you're reducing the risk for the astronauts on the surface.
Thank you so much for that, Cassandra. I do apologize to you and to our viewers, but we do have to end it here. We are at the top of the hour. Just a quick reminder to everybody to join us on February 25th. We have Mr. Donald Jantz, who is going to be talking to us about Alberta technology supporting the energy transition right here in Alberta. But please join me in thanking Dr. Marion for this incredible and very stimulating conversation, and we hope to have you back to explore some of these other rabbit holes, as you like to call them, but boy, are they incredible rabbit holes. Thank you so much, and thank you to all of you for joining us. I wish everyone an awesome rest of your day, and see you all here next month. Thank you.